Okay, this first graph is a semicircle, and it has a limited domain because of that square root. So the square root of 9 minus whatever this number is, it's got to be less than 9. So it cannot be greater than 9, otherwise we'll have the square root of a negative number, and that is not allowed in a function. So, for instance, putting a 4 in would give me 4 squared, which is 16. 9 minus 16 would not be allowed. So the number that I can put in would be 3, and even a negative 3. Negative 3 squared would give me a 9. So I can put in negative 3, negative 2, negative 1, 0, 1, 2, and 3. When I put a negative 3 in, I get 9 minus 9. Negative 3 squared is 9. 9 minus 9 is 0. The square root of 0 is 0. When I put a negative 2 in, let's put the negative 3, 0. When I put a negative 2 in, I get 9 minus 4. And the square root of 9 minus 4 is the square root of 5, which is a little bit more than 2. When I put a 1 in, 9 minus negative 1 squared would be the square root of 8, which is a little bit less than 3. When I put a 0 in, I get the square root of 9, which is 3. So 0, 3. When I put a 1 in, once again, I get the square root of 8. When I put a 2 in, I get the square root of 5. When I put a 3 in, I get 0. Now these 3 lattice points are the only 3 we really need because this is a semicircle. It's a half circle. Now the 9 gives us a hint as to what the radius of that circle is. So the center of the circle is at 0, 0, and the radius is going to be 3. So right 3, up 3, left 3. There we go. Okay. The rational function f of x equals 1 over x has a horizontal asymptote at y equals 0, and it has a vertical asymptote at x equals 0. If I put a negative 10 in for x, negative 10 in for x, I would have 1 over negative 10, which is negative 1/10. If I put a negative 5 in for x, I would have 1 over negative 5, which is negative 1/5. If I put a negative 2 in for x, I would have negative 1/2. If I put negative 1 in for x, I would have 1 over negative 1, which is negative 1. If I put negative 1/2 in for x, 1 divided by negative 1/2 is negative 2. If I put negative 1/5 in for x, I would have 1 divided by negative 1/5, which is negative 5. So what's going to happen is our points are going to form a curve that look just like that. And that's what happens when you put negative numbers in, not that, but that. So that's what's going to happen when we put negative numbers in for x. Now what happens if we put a 0 in? Well, you cannot divide by 0, so that would be undefined. What if I put in a positive 1/5? Well, 1/5, that would be 1 over 1/5, or 1 divided by 1/5, which is 5. So 1/5 would give me a 5 out. If we put a 1 in, 1 divided by 1, oops. Sorry, when you put 1/5 in, you get a 5 out. Yep, positive 1/5, comma 5. That's this part, that's that number right there. That's that ordered pair right there. When you put a 1 in, 1 divided by 1 is 1, you get a 1 out. When you put a 2 in, 1 divided by 2 is 1/2. When you put a 5 in, 1/5. When you put a 10 in, 1/10. So when you put positive values in for x, you end up in quadrant 1. So both parts of those curve make the rational function. And there's your curve. It's a curve in quadrant 1 and in quadrant 3, and it has this vertical asymptote and this horizontal asymptote. Okay, we have exponential function. If I put some negative values in, which I'm allowed, I'm going to get some fractions, and if I put positive numbers in, I'm going to feel a little bit more comfortable. I won't be getting fractions out. Exponential functions have a horizontal asymptote at y equals 0. When you put a negative 2 in, I would get 2 to the negative 2, which is 1/4. When I put a negative 1 in, I'd get 2 to the negative 1, which is 1/2. When I put a 0 in, 2 to the 0 is 1. When I put a 1 in, 2 to the first power is 2. When I put a 2 in, 2 squared is 4. When we put a 3 in, 2 cubed is 8. This graph has 1, 2, 3, 4 lattice points, and then I usually put 1 or 2 more points so that I have a nice little target to create my curve. Now log base 2 of x is the inverse of y equals 2 to the x. So number 9 and number 10 are inverses of one another. And when you have inverses of one another, the ordered pairs are flipped. So this ordered pair is 3, 8. This one is 2, 4. This one is 1, 2. And this one is 0, 1. A logarithmic function has a vertical asymptote. 0, 1 on the exponential is going to become 1, 0 on the log. 1, 2 on the exponential is going to become 2, 1 on the log. 2, 4 becomes 4, 2, and 3, 8 becomes 8, 3. And that's your logarithmic function. And both 9 and 10 are a base 2. Your exponential and logarithmic can be any base, but we typically show our parent functions with base 2. Now our natural exponential is a base e. E is approximately 2.718. So when I put in a negative 1 for x, I get 1 over 2.7-ish, which is a small fraction. It's a small decimal, it's a small number. So again, we have that horizontal asymptote, and we're going to have negative 1 and a very small number. When we put a 0 in, e to the 0 is 1. When we put a 1 in, e to the first power is about 2.7. Sometimes I say 2.7-ish. And when I put a 2 in, e squared, which would be 2.7 squared, is about 7.3-ish. Sometimes I just say ish because I say, well, if you make the dot big enough, nobody really can tell if it's 7.3 or 7.4. And that's what our natural exponential function looks like. So these points are very important. So 2, 7.3-ish, 1, 2.7-ish, and then 0, 1. Now on the natural log function, number 11 and 12 are inverses of one another. So the logarithm is going to have a vertical asymptote at x equals 0. And my ordered pairs, instead of 0, 1, we'll have 1, 0. Instead of 1, 2.7, we'll have 2.7, 1. And instead of 2, 7.3, we'll have 7.3-ish, 2. And that's what our logarithmic function looks like that has a base e. So those are our parent functions. And you should be able to reproduce these pretty quickly. So I would say maybe 20 to 30 seconds to do each one. So important that you're not having to create these tables to reproduce them. I'll make another video where I actually show you me creating the graphs very quickly so that you can get an idea of how quickly you should be able to make these graphs on your own to be successful in higher mathematics.